Good morning, professors. I'm Mac Whitehoe with registration number 60077. My topic is Be a Smart Banker, a research on one versus one gambling. So why do I choose gambling as my research topic? In those films about gambling, characters often bluff his opponents and they usually wins at the end. Is that true in reality? Therefore, my goal in the research is to determine whether bluffing can increase the gain of a person or not. If yes, how to bluff then? So let me introduce the game that I have investigated. First, two people are involved in the game, banker and player. And at the beginning, they need to put $R as the stakes. And each of them will receive a number from 0 to 1 inclusively. Let the number drawn by banker be x and that of player be y. Notice that x is not equal to y. And after that, banker should decide he will raise or not to raise. And in this case, banker do not raise. So the person who receives a bigger number will be the winner. And in this case, player is the winner, and he can take away all the stacks. What happens if banker chooses to raise? If banker chooses to raise, he needs to put $R as the stacks. And after that, player will decide he will fold or call. And in this case, player fold. And banker will be the winner automatically, no matter what the values of x and y are. And actually, banker benefits from this rule. If banker raises when he receives a small number, player may think that banker receives a large number, and banker will fold. Therefore, banker wins and gains even though he gets a small number. And the last case is banker raise and player call. If player call, he needs to put $R as the additional amount of stacks. And the person who received the bigger number will be the winner. And in this case, player is the winner and he can take away all the stacks. Mathematically, it is a maximum problem, minimizing the profits of banker by player strategy and maximizing it with respect to banker strategy. So I let Qx be a strategy function of banker. When banker receives a number x, Qx is the probability that he will raise. And Py be a strategy function of player. When player receives a number y, Py is the probability that he will call. So imagine that you're a banker. If you receive a number 0.1, will you raise? How about the number is 0.5 or 0.9 then? So let's find the answer and have a lesson on how to be a smart banker. And in part 1 of the presentation, I've assumed Qx is in this shape. We have defined Qx is equals to 1 when x is between 0 and m or n to 1 inclusively, and 0 to be otherwise. And I will call this strategy be bluffing strategy. And player strategy is shown as this. Py is equals to 1 when y is between c and 1 inclusively and 0 when otherwise. And I will call this strategy be calling strategy. So by the idea of two persons zero-sum game, I can rewrite the game that I have investigated into this table. And my goal is to find n and c. So solving this maximum problem is the same as finding the intersection of these two functions. And that is the answer of the maximum problem. So here are the strategy of bankers. Bankers should set m and n like this. And player should set c into this range such that he can minimize his loss. So the gain of a banker is R over R squared plus 5R plus $4. Notice that this value attains maximum when R is equals to 2, and where the gain is 1 over 9. Therefore, R should not be a very large number. So in part 2, I have another question. Can banker gain more if the strategy can be a mixed strategy? So the problem can be expressed as follows. Minimizing the profits of banker by C and maximizing it with respect to Qx. Can banker gain more if Qx is look like this mixed strategy? So I can rewrite the expected value of banker by using integrals. Take the first one as the example. 1 minus Qx is the probability that banker does not raise. And 1 minus x is the probability that x is smaller than y. And in this case, banker lose $1. Therefore, the expected value of banker is the weighted sum of the integrals times the gain. So after simplification, E can be expressed like this. And it is a convex function with respect to C. So E attains minimum when C fulfills dE dC equals to 0. And I let this value be C0. So a ratio formula can be derived. It tells us that C0 is a value divides the area under Qx into a ratio. Just like in the screen as shown, A to B is equals to R to R plus 2. So by using the ratio formula, E can be rewritten as these integrals. And notice that C0 depends on Qx. Therefore, C0 is a variable. Calculus of variation cannot be used because the limits in the integrals, the limits of integrals consist of variable. Therefore, I will try to solve the problem by another approach. That expression consists of xqx, and it is about the moment in the physics. So I will qx by center of mass. Therefore, I will let x1 and x2 bar like this, and rewrite the integrals like this. Therefore, to maximize E is the same as minimize x1 bar and maximize x2 bar. And therefore, qx will have this change. And the best qx, that is the player strategy, is reduced to a pure strategy, and it is the same as the first strategy. And so, among all players, bank strategy, pure strategy is the best strategy in attaining the maximum gain of banker. So, if the player, how can I minimize my loss if I'm not restricted to use the coin strategy? Can player lose less when PY is low like this? So my problem is to solve the maximum problem, that is minimizing the profits of banker by PY and maximizing it with respect to QX. Well, in this case, banker and player can be a mixed strategy. Therefore, again, rewrite the expected values of banker in terms of integrals. Notice that only those circle integrals are considerable. Others cannot, since their values won't change to player's decision. So, if I want to minimize E with respect to PY is the same as minimize those integrals. And here I have this. And I let Fy use integral inside square brackets. And actually, Py can change if we look at the property of Fy. Py should be as large as possible and hence is 1 when Fy is negative and Fy0 when Fy is positive in order to match the set value. For example, if Fy is okay this as this. Therefore, after some investigation, I found that Fy is a decreasing function from positive to negative. Therefore, it must cut the as a point and say that point is A. And therefore, Py is reduced to this shape, and it is the same as the coin strategy. Therefore, the best play strategy, the coin strategy, is that the player should use the coin strategy in order to minimize his loss. So I have solved the psychological problems by mathematics. Gain fluent can really increase the gain of a person. So here are the research direction, and it is by running the gain. So the further developments that I'm going to show. And here is the further development. After player calls, I will introduce another new set of rules. Player can choose to raise or not to raise, and I will call the probability that banker player raise will be P2Y. And if I choose not to raise, things reduce to what I have investigated before. If player chooses to raise, he needs to put outdoor as the additional amount of stacks. So after banker will fold, and I let Q2 be the probability that banker will call. If banker fold, he will lose automatically. And if banker call, he needs to put outdoor as the additional stacks. And the person receiving a bigger number will be the winner. So my problem is not min and min-max problem. And here are the shape of those four strategy functions. Those I cannot figure out the